Beyond the edge of our solar system, an array of extraordinary and mysterious worlds exists. These distant planets challenge our understanding of what a world can be. Some are rocky and Earth-like, residing in the habitable zones of their stars where liquid water could flow. Others are gas giants, larger than Jupiter, with atmospheric conditions so extreme they boggle the mind. There are worlds with endless oceans, planets where diamonds rain from the sky, and places where life as we know it might find a way to thrive in the most unexpected environments. Join us as we travel beyond our solar system and explore the strange worlds that could become our next home. Proxima Centauri B lies tantalizingly close to us in cosmic terms, orbiting the red dwarf star Proxima Centauri, which is part of the Alpha Centauri star system. This star system is located approximately 4.2 light-years away from our own solar system, making it the closest extrasolar system to Earth. Nestled in the constellation of Centaurus, Proxima Centauri B resides within the Milky Way galaxy, specifically in the Orion arm, just as our solar system does. This proximity has given scientists and astronomers a unique opportunity to study an exoplanet that might be similar in some ways to Earth. This intriguing exoplanet, Proxima Centauri B, orbits its parent star at a distance of just 4 million miles, which is a mere fraction of the 93 million miles between Earth and the Sun. Given this proximity, it completes a full orbit approximately every 11 days. Despite its nearness to a faint red dwarf star, Proxima Centauri B is of significant interest because it resides in the habitable zone, where conditions might be right for liquid water to exist. This has spurred ongoing discussions and investigations about its potential to support life, capturing the imagination and curiosity of both scientists and the public alike. And speaking of capturing imagination and curiosity, if you're fascinated by the complexities of celestial mechanics and the possibilities of life beyond Earth, Brilliant.org offers a way to dive even deeper into these topics. Brilliant transforms complex scientific concepts into engaging, hands-on learning experiences that everyone can enjoy. Whether you're a professional or a curious learner, Brilliant's interactive lessons make mastering the fundamentals of science and technology both accessible and enjoyable. Currently, I'm taking Brilliant's course on how LLMs work, exploring the advanced mechanics of language models in AI. This is just one example of how Brilliant's courses bring complex ideas to life through interactive exercises and visual learning, perfect for anyone fascinated by the predictive patterns used not only in AI, but in studying orbital mechanics like those of Proxima Centauri B. So, whether you're passionate about uncovering the secrets of space or the latest innovations in science and technology, Brilliant gives you the tools you need to explore and understand the universe's deepest mysteries. Start your free 30-day trial today by visiting brilliant.org/spacedust. Plus, if you decide to continue, you'll receive 20% off an annual premium subscription. Discover the thrill of learning with Brilliant and see the universe in a new light. Click the link in the description to begin your adventure in learning today. Proxima Centauri B becomes a candidate for habitability, primarily because it orbits within the habitable zone, often referred to as the Goldilocks zone, of its parent star, Proxima Centauri. This is the range of distances from a star where conditions might be just right, not too hot and not too cold, for liquid water to exist on a planet's surface. Since water is essential for life as we know it, a planet positioned within this zone sparks significant scientific interest. Proxima Centauri B sits at an ideal distance from its star, suggesting that under the right atmospheric conditions, it could maintain water in liquid form, a pivotal ingredient for life to potentially develop and thrive. Additionally, Proxima Centauri B has a mass that is at least 1.2 times that of Earth. This suggests it could have a rocky composition, similar to our own planet, providing a solid surface where water, if present, could pool and form oceans or lakes. Scientists have also hypothesized about the possibility of an atmosphere that could protect the planet's surface from stellar radiation and help regulate temperatures, although this remains speculative without direct observational evidence. Its mass and location within the habitable zone, combined with ongoing technological advancements in exoplanetary exploration, make Proxima Centauri B a tantalizing candidate in the search for extraterrestrial life. The proximity of Proxima Centauri B to its star, Proxima Centauri, dramatically influences its climate and environmental conditions. Orbiting a scant 4 million miles away, the planet is much closer to its star than Earth is to the Sun, completing a full orbit in just about 11 Earth days. This close orbit means that Proxima Centauri B experiences an intense level of stellar radiation and gravitational interaction. One significant consequence of this close orbit is the possibility of tidal locking, where one side of the planet perpetually faces the star while the other side remains in constant darkness. If tidal locking has occurred, it would result in extreme temperature variations, with one hemisphere being incredibly hot and the other frigidly cold, potentially affecting the planet's ability to support life. Moreover, Proxima Centauri, being a red dwarf star, is known for its stellar flares and high levels of stellar activity. This can result in bursts of ultraviolet radiation and charged particles that could strip away the planet's atmosphere over time or significantly alter its composition. However, if Proxima Centauri B possesses a strong magnetic field, akin to Earth's, it might deflect some of this stellar radiation, thereby preserving its atmosphere and allowing for a more stable climate. The precise impact of these factors on Proxima Centauri B's climate remains a subject of active research and debate within the scientific community, as they attempt to unravel the complexities of conditions on this nearby exoplanet. Proxima Centauri B was detected using a combination of sophisticated astronomical techniques that have revolutionized the search for exoplanets. The primary method that led to its discovery is the radial velocity method, also known as Doppler spectroscopy. This technique involves observing the star Proxima Centauri and detecting minute wobbles in its motion caused by the gravitational pull of an orbiting planet. As Proxima Centauri B orbits its star, it induces a slight but measurable shift in the star's light spectrum. These shifts correspond to the star moving towards and away from us, providing clues about the planet's existence, its mass, and its orbital period. Another vital method that supported the discovery is astrometry, which involves precise measurements of a star's position in the sky. Over time, astronomers can observe small changes in the star's position caused by the gravitational pull of the orbiting planet. While this method is extremely challenging due to the minute displacements involved, advancements in technology and observational accuracy have bolstered its efficacy. Additionally, transit photometry, although not directly responsible for the discovery of Proxima Centauri B in this case, is often used to detect exoplanets by measuring dips in a star's brightness as a planet passes in front of it. Together, these methods offer a multifaceted approach to detecting and confirming the presence of planets around other stars, painting a clearer picture of our galactic neighborhood. Future missions to Proxima Centauri B face a myriad of formidable challenges, ranging from technological limitations to the vast distances involved in interstellar travel. Firstly, the distance from Earth to Proxima Centauri B is approximately 4.2 light-years, which equates to nearly 25 trillion miles. With current propulsion technology, it would take tens of thousands of years for a spacecraft to reach this distant exoplanet. Therefore, developing advanced propulsion systems that can achieve a significant fraction of light speed is imperative for making such a mission feasible within a human lifetime. Another significant challenge lies in protecting any interstellar probe or crewed mission from the harsh conditions of space. The journey involves exposure to cosmic radiation, high-energy particles, and interstellar dust, all of which could potentially damage spacecraft instruments and endanger human life. Effective shielding and autonomous systems capable of repairing and maintaining a long-duration mission will be crucial. Additionally, navigation and communication over such vast distances present unique difficulties, requiring innovations in deep space communication technology to ensure continuous contact and data transmission back to Earth. Moreover, once at Proxima Centauri B, there will be the task of studying its environment closely. The planet's close proximity to its parent star means it may experience intense stellar radiation and potentially unstable surface conditions due to tidal locking. Instruments must be robust enough to survive and function in these harsh environments while collecting meaningful data. Considering these extensive challenges, Interstellar exploration missions to Proxima Centauri B will demand unprecedented advancements in space technology and a new era of innovation in human ingenuity. Kepler 186f stands out in the realm of exoplanetary science due to a combination of its Earth-like size and its location within the habitable zone of its host star, a red dwarf named Kepler 186. Discovered by NASA's Kepler Space Telescope in 2014, Kepler 186f is approximately 500 light-years away from Earth in the constellation Cygnus. What makes Kepler 186f particularly remarkable compared to other exoplanets in the habitable zone is its radius, which is only about 10% larger than Earth's. This near-Earth size increases the probability that Kepler 186f might have a rocky composition, similar to Earth, rather than being a gas giant like many other exoplanets. Additionally, Kepler 186f orbits its star at a distance that places it within the habitable zone, where temperatures could allow for liquid water to exist on its surface. It completes an orbit around its star roughly every 130 days. Kepler 186f star, although cooler and less luminous than our Sun, provides just enough warmth to potentially sustain liquid water, given the right atmospheric conditions. This distance offers a delicate balance, reducing the risks of extreme temperatures that can be found on planets either too close or too far from their stars. This unique combination of size and habitable zone positioning sets Kepler 186f apart as one of the leading candidates in the ongoing search for potentially habitable exoplanets. Kepler 186f orbits a star known as Kepler 186, which differs significantly from our Sun in several key ways. Firstly, Kepler 186 is a red dwarf, scientifically categorized as an M-dwarf star. This type of star is both smaller and cooler than our G-type main sequence star, the Sun. Specifically, Kepler 186 has roughly half the mass and about half the radius of the Sun. Because of these dimensions, a red dwarf like Kepler 186 emits much less light and heat. This lower luminosity means the habitable zone around Kepler 186 is much closer to the star compared to the habitable zone surrounding the Sun. Another critical difference lies in the lifespan and stellar activity of these stars. Red dwarfs like Kepler 186 have much longer lifespans than stars like the Sun, potentially billions of years longer, because they burn their fuel more efficiently and at a slower rate. However, red dwarfs are also notorious for their high levels of stellar activity, especially in their younger years. This activity includes frequent and potent stellar flares, which can emit intense bursts of ultraviolet and X-ray radiation. Such flares can strip away or negatively affect the atmospheres of orbiting planets, influencing their capacity to support life. While Kepler 186f star is cooler, smaller, and less bright than our Sun, it may offer a stable environment for an extended period, despite its occasional high-energy outbursts. Understanding these stellar characteristics helps astronomers assess Kepler 186f's potential habitability and its differences from Earth-like planets within our own solar neighborhood. Kepler 186f holds a special place in the search for Earth-like planets, serving as an exciting milestone in our quest to find habitable worlds beyond our solar system. Discovered by NASA's Kepler Space Telescope in 2014, it was the first exoplanet found within the habitable zone of its star to have a size similar to Earth. This discovery fueled considerable excitement because it suggests that Earth-sized planets in habitable zones where conditions might be right for liquid water could be more common than previously thought. The significance of Kepler 186f extends beyond its individual characteristics. It has helped refine our understanding and techniques in planetary detection and habitability assessment. By confirming the existence of a near-Earth-sized planet in the habitable zone of a red dwarf star, Kepler 186f has broadened the scope of where we might find potentially habitable planets. It demonstrated the efficacy of transit photometry, a method where periodic dips in the star's brightness reveal the presence of an orbiting planet, in detecting such worlds. Kepler 186f has also encouraged astronomers to intensify their search around red dwarf stars, which constitute the most common type of star in our galaxy, thereby expanding the potential field of study for habitable exoplanets. Furthermore, the discovery of Kepler 186f has paved the way for future missions and advanced telescopes aimed at finding and studying more Earth-like planets. It exemplifies the importance of continually improving our observational techniques and expanding our search criteria, fostering the hope that one day we might discover a planet with conditions even more closely mirroring those of Earth. Kepler 186f continues to inspire scientific inquiry and public imagination, underscoring the profound questions about life's potential existence elsewhere in the universe. Kepler 186f was discovered through the meticulous observations made by NASA's Kepler Space Telescope, which employed the transit photometry method to detect exoplanets. This technique involves continuously monitoring the brightness of stars to detect periodic dips in light intensity, which indicate that a planet is passing or transiting in front of the star from our perspective on Earth. When Kepler 186f crosses in front of its host star, Kepler 186, it causes a slight but measurable reduction in the star's brightness. These subtle changes in luminosity were detected by the Kepler telescope, allowing astronomers to infer the presence of the planet. The discovery process wasn't instantaneous. The data collected by Kepler required careful analysis to distinguish between genuine planetary transits and other astrophysical phenomena or noise. Multiple transits were observed over time to confirm the periodicity and consistency of the dips in brightness, ensuring that the detected signal was indeed caused by an orbiting planet. In the case of Kepler 186f, the transit data revealed that the planet orbits its star approximately every 130 days and has a radius about 10% larger than Earth's. Following the initial detection, additional observational data and rigorous modeling were employed to confirm the planet's existence and to estimate its size and orbital characteristics. The confirmation of Kepler 186f marked a significant achievement for the Kepler mission, as it demonstrated the potential for discovering Earth-sized planets in habitable zones around their stars, significantly advancing our understanding of where life-supporting conditions might exist beyond our solar system. Kepler 186f's potential for hosting liquid water hinges on several critical factors, beginning with its location in the habitable zone of its host star, Kepler 186. This region, often referred to as the Goldilocks zone, is the orbital distance where a planet could have the right conditions for water to remain in liquid form, neither too hot nor too cold. For Kepler 186f, this zone allows the possibility that, under the right atmospheric conditions, surface temperatures might support liquid water, which is a key ingredient for life as we know it. However, the mere position within the habitable zone doesn't guarantee the presence of liquid water. The planet's atmosphere plays a crucial role in regulating surface conditions. If Kepler 186f possesses an atmosphere with sufficient greenhouse gases, much like Earth's, it could trap heat and maintain surface temperatures within a range that allows liquid water to exist. Without a significant atmosphere, the planet could be too cold, especially on the side facing away from its star, assuming it experiences tidal locking, where one side is perpetually dark. Conversely, too thick an atmosphere might lead to extreme greenhouse effects, giving rise to scorching surface temperatures as seen on Venus. Another aspect lies in the star's activity. Kepler 186 is a red dwarf, which can emit strong stellar flares. These flares could strip away or significantly alter the composition of the planet's atmosphere over time, potentially impacting its ability to retain liquid water. Because Kepler 186f orbits relatively close to its star, any atmospheric retention and surface conditions would be highly influenced by the star's behavior. While Kepler 186f's position within the habitable zone provides a tantalizing possibility for liquid water, the actual conditions depend on factors like atmospheric composition and stellar activity. Future missions equipped with advanced telescopes aimed at atmospheric analysis will be pivotal in determining whether Kepler 186f and others like it truly have the potential to support liquid water and, by extension, life. The TRAPPIST-1 system, located approximately 39 light-years away in the Aquarius constellation, consists of 7 known Earth-sized exoplanets. These planets orbit a single ultra-cool dwarf star named TRAPPIST-1. What's particularly fascinating about this planetary system is the high potential for habitability, as well as the close orbits of these planets to their host star, making them excellent candidates for studying planetary formation and the possibility of life beyond our solar system. Among these 7 planets, TRAPPIST-1e stands out as particularly intriguing. It is considered one of the most Earth-like of the group, primarily due to its location within the habitable zone of the TRAPPIST-1 star. The habitable zone is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. TRAPPIST-1e's size and density are similar to Earth's, suggesting it has a rocky composition which is essential for the potential development and retention of a stable atmosphere. Moreover, TRAPPIST-1e has optimal conditions compared to its siblings because it receives a level of stellar radiation and warmth comparable to what Earth receives from the Sun. This balance makes it less likely to experience the extreme conditions found closer to or farther from the central star. The planet's equilibrium temperature, a measure of the surface temperature assuming a perfect balance between received and emitted energy from the star, also points to the possibility of maintaining liquid water. This combination of factors makes TRAPPIST-1e a prime target for future studies aiming to detect signs of atmospheric composition, water presence, and possibly even biosignatures, enhancing our understanding of the potential for life on exoplanets. Understanding the key features of TRAPPIST-1e's atmosphere is crucial, but it's important to note that current observations are still in the preliminary stages. Nonetheless, scientists have made some educated guesses based on the planet's size, density, and location within the habitable zone of the TRAPPIST-1 star. TRAPPIST-1e is thought to have an atmosphere that could be conducive to supporting liquid water, primarily if it contains the right mix of gases. One of the main hypotheses is that TRAPPIST-1e might possess an atmosphere with a composition similar to Earth's, rich in nitrogen and oxygen. Such an atmosphere would be crucial for maintaining surface pressure conducive to liquid water. The presence of greenhouse gases like carbon dioxide could help retain heat, preventing the planet from freezing despite the dimmer light of its ultra-cool dwarf star. However, this balance is delicate. Too much greenhouse effect could lead to runaway heating, while too little could result in a frozen world. Key features also include the potential presence of water vapor. Detection of water vapor in the atmosphere would be a significant indicator of the planet's ability to host liquid water on its surface. Advanced telescopes, such as the James Webb Space Telescope, are anticipated to provide more detailed observations in the near future, allowing scientists to analyze the atmosphere's composition for water vapor, methane, and other potential biomarkers. Atmospheric dynamics are another crucial aspect. TRAPPIST-1e might be tidally locked, meaning one side of the planet always faces the star, leading to extreme temperature gradients between the day and night sides. The atmosphere's ability to circulate heat effectively between the two hemispheres could play a pivotal role in stabilizing the climate. Future research will focus on these atmospheric characteristics to paint a clearer picture of TRAPPIST-1e's potential to support life. TRAPPIST-1e stands out as a top candidate in the search for extraterrestrial life due to several compelling factors that elevate its potential for habitability. First and foremost, its location within the habitable zone of the TRAPPIST-1 star is a significant factor. This zone is where conditions are just right for liquid water to exist on a planet's surface. Liquid water is essential for life as we know it, and TRAPPIST-1e's position offers a potential balance of temperature that could sustain such conditions. Another critical factor is TRAPPIST-1e's Earth-like size and density. It is roughly the same size as Earth and has a similar composition, suggesting it is a rocky planet. This is important because a rocky surface is necessary for the cycle of nutrients and the retention of an atmosphere, both of which are vital for supporting life. The planet's gravity, akin to Earth's, is likely sufficient to hold onto an atmosphere, crucial for maintaining liquid water and protecting potential life forms from harmful stellar radiation. Furthermore, the TRAPPIST-1 system's proximity to Earth at just 39 light-years away makes it accessible for detailed study with current and next-generation telescopes. Instruments like the James Webb Space Telescope and other future observatories will be able to analyze the atmospheric composition of TRAPPIST-1e, searching for biosignatures, chemical indicators of life. These observations will aim to detect the presence of oxygen, water vapor, methane, and other gases that could suggest biological activity. Finally, the relatively stable nature of the TRAPPIST-1 star, an ultra-cool dwarf, provides a consistent source of energy over long periods, which is conducive to the development and sustenance of life. Though it may emit occasional flares, the lower overall energy output compared to larger stars reduces the risk of harmful radiation spikes that could strip away an atmosphere or sterilize the surface. TRAPPIST. 1e's optimal position within the habitable zone, Earth-like characteristics, and the feasibility of detailed observations make it an exceptionally promising candidate in the ongoing search for signs of extraterrestrial life. TRAPPIST. 1e orbits its star, TRAPPIST-1, at a much closer distance compared to the Earth-Sun distance. Specifically, TRAPPIST-1e lies about 0.028 astronomical units, AU, from its host star. An astronomical unit, or AU, is the average distance between the Earth and the Sun, roughly 93 million miles, or 150 million kilometers. In stark contrast, Earth orbits the Sun at 1 astronomical unit from it. The significant difference in these distances can be attributed to the nature of the stars involved. TRAPPIST-1 is an ultra-cool dwarf star, considerably smaller and cooler than our Sun. Because of its lower temperature and luminosity, the habitable zone around TRAPPIST-1 is much closer to the star. While Earth is situated at a comfortable distance from the Sun, to receive an optimal amount of solar energy to maintain liquid water and support life, TRAPPIST-1e needs to orbit much closer to its ultra-cool dwarf star to achieve similar energy levels. This close proximity to TRAPPIST-1 implies that TRAPPIST-1e completes an orbit around its star roughly every 6 Earth days. Despite this tight orbit, the star's low luminosity means that the radiation and energy received by TRAPPIST-1e are comparable to what Earth gets from the Sun. This proximity also suggests that TRAPPIST-1e could experience tidal locking, where one side of the planet constantly faces the star, resulting in distinct hemispherical climates, a hot day side and a cold night side. Whether or not TRAPPIST-1e can moderate these temperature extremes through atmospheric circulation is an intriguing subject for further research. The discovery of TRAPPIST-1, a potentially habitable exoplanet within the TRAPPIST-1 system, was made possible through a synergy of groundbreaking technologies and methodologies in modern astronomy. The primary instrument was the Transiting Planets and Planetesimals Small Telescope, better known as TRAPPIST, located in Chile. This small but powerful telescope specializes in the transit method, where it meticulously observes the subtle dimming of a star's light as planets pass in front of it. The discovery was further solidified and expanded upon using the Spitzer Space Telescope. With its infrared capabilities, Spitzer provided more detailed observations by continuously monitoring the faint light variations and enabling a clearer understanding of the planetary compositions and orbits. In addition to these telescopes, advanced data processing algorithms and techniques were crucial. Sophisticated software analyzed the vast amounts of data collected, identifying periodic dips in the star's light indicative of planetary transits. Furthermore, the High-Accuracy Radial Velocity Planet Searcher, or HARPS, played a significant role in confirming the planet's existence and providing accurate measurements of its mass and orbit. The collaborative effort across multiple observatories worldwide, synergized with numerical modeling and simulations, allowed astronomers to deduce details about TRAPPIST-1e's potential atmosphere and habitability. These technological advancements together represent a remarkable leap in our ability to detect and study distant exoplanets, inching us closer to answering the age-old question, are we alone in the universe? The historical significance of 51 Pegasi b in the context of exoplanet discovery cannot be overstated. In October 1995, astronomers Michel Mayor and Didier Queloz announced their groundbreaking discovery of this planet orbiting the star 51 Pegasi, situated approximately 50 light-years away in the constellation Pegasus. This discovery marked the first confirmed detection of an exoplanet orbiting a Sun-like star, sparking an astronomical revolution. Prior to this, exoplanet discoveries were confined to pulsar planets, which orbit around dense remnant cores of dead stars, and had limited implications for the study of planetary systems as a whole. The identification of 51 Pegasi B revealed the existence of planetary bodies around stars similar to our own, changing the landscape of astrophysics and fueling a surge in the search for alien worlds. Coined as a hot Jupiter, 51 Pegasi B defied preconceptions about planetary formation and dynamics. Its close proximity to its host star, completing an orbit in just 4 Earth days, challenged existing theories that gas giants could only form and remain at more considerable distances from their stars. This unexpected find led to new models of planetary migration and behavior, promoting a reconsideration of how planetary systems could evolve. Furthermore, it highlighted the capabilities of the radial velocity method, which detects planets by noting the small wobbles induced in a star by an orbiting planet's gravitational pull. This breakthrough paved the way for the discovery of thousands of exoplanets in the decades that followed, transforming our understanding of the universe and our place within it. The term hot Jupiter describes exoplanets that share several defining characteristics with 51 Pegasi B. First and foremost, 51 Pegasi B is a gas giant, similar in composition and size to Jupiter, our own solar system's largest planet. However, what sets it apart and earns it the hot prefix is its extremely close proximity to its host star, 51 Pegasi. Unlike Jupiter, which resides about 5 astronomical units, AU, from the Sun, 51 Pegasi B orbits its star at just 0.05 AU, a mere 1/20th of the distance from Earth to the Sun. This extraordinarily tight orbit results in searing temperatures estimated to be around 1,000 degrees Celsius, a stark contrast to the much cooler temperatures on Jupiter. Another hallmark of 51 Pegasi B's hot Jupiter classification is its rapid orbital period. The planet completes a full orbit around 51 Pegasi in just over 4 Earth days, indicative of the strong gravitational pull exerted by being in such a close orbit. This fast-paced revolution not only exposes the planet to intense stellar radiation, but also often leads to tidal locking, where one side of the planet constantly faces the star, creating a scenario where one hemisphere continuously bakes while the other endures perpetual night. These extreme conditions pose fascinating questions about atmospheric dynamics and potential weather patterns on such planets. The discovery and classification of 51 Pegasi B as a hot Jupiter have propelled the understanding of planetary systems, revealing the myriad forms and arrangements that planets can take beyond our solar system. The discovery of 51 Pegasi B fundamentally altered our understanding of planetary systems in several profound ways. Firstly, it shattered the preconceived notion that gas giants could only form and remain at great distances from their parent stars, as exemplified by our own solar system's Jupiter. This exoplanet, orbiting its star at a mere 0.05 astronomical units, demonstrated that large gas giants could exist in extremely close proximity to their stars, a concept that was previously unimaginable. This prompted astronomers to re-evaluate existing models of planetary formation and migration. Current theories now incorporate the idea that newly formed gas giants can migrate inward from their initial positions, influenced by gravitational interactions with the protoplanetary disk and other bodies within the system. Furthermore, the successful use of the radial velocity method in discovering 51 Pegasi B provided a robust and highly efficient technique for detecting other exoplanets. The method's ability to measure the tiny wobbles in a star caused by the gravitational pull of orbiting planets presented a new, practical approach to planet hunting. Before this breakthrough, techniques for discovering exoplanets were limited and lacked precision. The detection of 51 Pegasi B validated the radial velocity method's effectiveness and spurred a wave of exoplanet discoveries, uncovering thousands of planets of varying sizes, compositions, and orbital characteristics. Lastly, the discovery opened the floodgates for the identification of entirely new classes of exoplanets, including super-Earths and mini-Neptunes. It broadened our perspective on the diversity and complexity of planetary systems, illustrating that our solar system's architecture, once thought to be a universal blueprint, is just one of many possible configurations. This paradigm shift has fueled advancements in telescope technology and space missions dedicated to surveying exoplanets, ultimately encouraging a more comprehensive quest to understand the vast, varied planetary arrangements that exist in the universe. The atmospheric conditions on 51 Pegasi B are notably unique and extreme, a result of its classification as a hot Jupiter. Due to its proximity to its host star, 51 Pegasi, the planet endures searing temperatures that can reach up to approximately 1,000 degrees Celsius. This intense heat has profound effects on its atmosphere, likely leading to the presence of ionized metals and a range of exotic chemical reactions uncommon in cooler, more distant planets. Spectroscopic observations suggest that the atmosphere may contain high concentrations of elements like sodium and potassium, which are more detectable in such high-temperature environments. Moreover, the likelihood of 51 Pegasi B being tidally locked, with one side perpetually facing the star and the other shrouded in darkness, creates intriguing weather phenomena. The stark temperature contrast between the day side and the night side could drive supersonic winds, redistributing heat and influencing atmospheric dynamics in ways that are still not fully understood. The atmosphere's composition and behavior under these extreme conditions offer valuable insights into the physics of atmospheric circulation and heat transfer on exoplanets. Observations from instruments such as the Hubble Space Telescope's spectrograph continue to refine our understanding of this alien world's atmospheric characteristics, highlighting the unexpected complexity and diversity of exoplanet atmospheres. When comparing 51 Pegasi B to Jupiter in our solar system, several key differences and similarities become apparent, highlighting the diversity among gas giants. Starting with their sizes, both are broadly similar in terms of mass and radius, with 51 Pegasi B having approximately half the mass of Jupiter. However, their orbital characteristics diverge dramatically. While Jupiter orbits the Sun at a distance of about 5 astronomical units, 51 Pegasi B orbits its host star, 51 Pegasi, at a mere 0.05 astronomical units. This close proximity results in 51 Pegasi B completing an orbit in just over 4 Earth days, in stark contrast to Jupiter's leisurely 12-year orbital period. The temperature difference between the two planets is another striking contrast. Jupiter, situated far from the Sun, has an average cloud-top temperature of about -145 degrees Celsius. In contrast, 51 Pegasi B, often referred to as a hot Jupiter, experiences scorching atmospheric temperatures around 1,000 degrees Celsius. This intense heat influences the composition and behavior of 51 Pegasi B's atmosphere, likely leading to the presence of exotic chemicals, ionized metals, and high-altitude clouds, none of which are present in Jupiter's cooler environment. Additionally, the potential tidal locking of 51 Pegasi B, where one side perpetually faces its star, creates conditions for extreme weather patterns, such as supersonic winds that redistribute heat across the planet's atmosphere. Despite these differences, both planets share similarities in their gas giant nature. They lack a solid surface and are composed predominantly of hydrogen and helium. Their substantial masses exert a significant gravitational influence within their respective systems. The comparison underscores the diversity of planetary systems and enriches our understanding of the range of environments in which gas giants can exist, from the cold, distant reaches of our solar system to the scorching, close-in orbits of distant stars. Kepler 22b holds a unique position within the pantheon of exoplanets due to its location in the habitable zone, the region around a star where conditions might be just right for liquid water to exist on a planet's surface. This habitable zone, often referred to as the Goldilocks zone, is neither too hot nor too cold, but just right. Discovered by NASA's Kepler Space Telescope, Kepler 22b orbits its host star Kepler 22 at about 0.85 astronomical units placing it comfortably within this life-friendly region. What makes Kepler 22b particularly intriguing is that its parent star is quite similar to our Sun, though slightly smaller and cooler, which contributes to a stable, consistent energy output, conducive to maintaining favorable conditions for water-based life. Adding to its uniqueness, Kepler 22b is notable for its size, which is about 2.5 times the radius of Earth. This makes it one of the first super-Earths discovered within a habitable zone. Its size raises fascinating questions about its potential composition, whether it might be an Earth-like rocky planet with a substantial atmosphere, or perhaps a mini Neptune with a thick envelope of gases. While its exact nature remains under investigation, the planet's equilibrium temperature, estimated to be around 22 degrees Celsius, aligns tantalizingly with human habitable needs, assuming a similar atmospheric makeup to Earth. This discovery tantalizes scientists with the possibility of finding a world with conditions suitable for life, either of microbial or even more complex forms, in a stellar setup not unlike our own solar neighborhood. Kepler 22b stands out in contrast to Earth primarily due to its significantly larger size. With a radius approximately 2.5 times that of Earth, Kepler 22b falls into the category of super-Earths, a classification denoting planets larger than Earth but significantly smaller than the gas giants like Neptune and Uranus. This size difference implies that Kepler 22b has a much greater volume and potentially a higher mass, likely resulting in stronger gravitational pull at its surface. However, the exact mass of Kepler 22b remains less certain, as its discovery was primarily based on the transit method, which provides information about the planet's size but not its mass. The implications of Kepler 22b's larger size are profound. If it shares a similar rocky composition with Earth, its higher volume could mean a more substantial atmosphere and dynamic geological activity due to intense internal pressures. Alternatively, Kepler 22b might have a thick gaseous envelope, similar to a mini Neptune, which would place significant emphasis on understanding the planet's atmospheric composition and structure. In comparison, Earth's relatively thinner atmosphere and smaller size make it a compact, rocky planet with a well-balanced climate system that supports a diverse range of life. The study of Kepler 22b and other super-Earths offers invaluable insights into the diverse potential habitats in our galaxy and challenges our understanding of planet formation and sustainability of life in varying planetary conditions. Kepler 22b's potential for habitability lies in a combination of factors that make it an intriguing candidate for studying extraterrestrial life possibilities. Chief among these is its location within the habitable zone of its host star Kepler 22, a region where conditions could be suitable for the existence of liquid water, a fundamental ingredient for life as we know it. The planet's equilibrium temperature, estimated to be around 22 degrees Celsius, further bolsters the possibility of a temperate climate, conducive to maintaining water in liquid form, assuming an Earth-like atmospheric composition. However, the true potential for habitability depends on several crucial, yet still uncertain, parameters. Firstly, Kepler 22b's size, approximately 2.5 times the radius of Earth, implies a stronger gravitational pull, which could affect its atmospheric retention and surface conditions. If Kepler 22b is a rocky planet with a significant atmosphere, it might possess stable weather patterns and a climate framework capable of supporting life. On the other hand, if the planet has a thick Neptune-like gaseous envelope, it might be less suitable for life as we understand it due to high pressures and potentially hostile environmental conditions at the surface. The planet's potential habitability also hinges on its atmospheric composition. A dense atmosphere rich in greenhouse gases like carbon dioxide could lead to a runaway greenhouse effect, creating excessively hot surface conditions. Conversely, an atmosphere with a balanced mix of gases conducive to life, such as nitrogen, oxygen, and traces of carbon dioxide, would significantly enhance its habitability prospects. Until further observations can pinpoint these details, including advanced spectroscopy from telescopes like the James Webb Space Telescope, the exact habitability of Kepler 22b remains a tantalizing mystery. Despite these uncertainties, Kepler 22b stands as a prime target for the continuing search for life beyond Earth. spurring both scientific curiosity and technological advancements to unlock its secrets. Kepler 22b was detected using the transit method, a highly effective technique employed by NASA's Kepler Space Telescope, which was specifically designed to find Earth-like planets orbiting other stars. This method involves monitoring the brightness of stars over extended periods to detect periodic dips in light intensity. These dips occur when a planet passes in front of its host star from the perspective of the observer, an event known as a transit. During a transit, the planet blocks a small fraction of the starlight, causing a temporary and slight dimming that can be precisely measured. Kepler 22. B's detection began with the identification of such a transit event in the data collected by the Kepler Space Telescope. The telescope observed the star, Kepler 22, for over 3 years, capturing the subtle dimming caused by the planet's transit across the star's face. This event was recorded multiple times, at intervals consistent with the planet's orbital period of about 290 days. To confirm the planetary nature of the detected signal and rule out false positives that could mimic a transit, such as binary star systems or stellar variability, the initial transit findings were subjected to rigorous follow-up observations and analyses using other ground-based telescopes and additional measurements. The confirmation of Kepler 22b's existence involved analyzing the consistency and depth of the transit signals, as well as refining the planet's estimated size and orbit. Through sophisticated algorithms and cross-referencing with models of planetary transits, astronomers were able to confirm that Kepler 22b indeed orbited within the habitable zone of its host star. This discovery marked a significant milestone as one of the first potentially habitable super-Earths identified using the transit method, showcasing the immense potential of this approach in expanding our knowledge of distant worlds. Kepler 22b has played a pivotal role in advancing exoplanet research, particularly in the context of identifying potentially habitable worlds beyond our solar system. As one of the first confirmed exoplanets found within the habitable zone of its host star, its discovery marked a significant milestone in the search for Earth-like planets. This finding underscored the effectiveness of the Kepler Space Telescope and the transit method for detecting distant planets. By presenting evidence that planets could exist within habitable zones around Sun-like stars, Kepler 22b fueled optimism and refined strategies for subsequent exoplanet exploration missions. The discovery of Kepler 22b also catalyzed interest in studying super-Earths, planets larger than Earth but smaller than Neptune. Its size, roughly 2.5 times the radius of Earth, challenged existing theories of planet formation and habitability. Researchers began to explore the diversity of planetary types and conditions, broadening the scope of what constitutes a potentially habitable environment. The study of Kepler 22b led to advancements in atmospheric modeling and the refinement of criteria for habitability, incorporating factors like atmospheric composition, geothermal activity, and the potential for liquid water. Additionally, Kepler 22b's discovery highlighted the necessity for multi-method approaches in confirming exoplanets. While the transit method provided initial clues, follow-up observations and analyses were essential for verifying its characteristics and ensuring it wasn't a false positive. This collaborative approach set a precedent for future exoplanet research, emphasizing the importance of corroborative data from various observational platforms and techniques. Consequently, Kepler 22b has not only broadened our understanding of where habitable worlds might be found, but has also refined the tools and methodologies that astronomers use to explore the cosmos, paving the way for discoveries that may one day confirm the presence of life beyond Earth. Gliese 581g is one of the most debated exoplanets due to the controversy surrounding its very existence and its potential habitability. Discovered in 2010 by astronomers Stephen Vogt and R. Paul Butler, the initial announcement claimed that Gliese 581g, located around 20 light-years away in the constellation Libra, resided within the habitable zone of its red dwarf star, Gliese 581. The prospect of a potentially Earth-like exoplanet in a stellar habitable zone generated widespread excitement. as its size, approximately 3 to 4 times the mass of Earth, suggested it could have conditions suitable for liquid water and possibly life. However, subsequent analyses and observations cast doubt on the planet's existence. Independent research teams struggled to confirm the detection using the radial velocity method, which measures wobbles in a star caused by the gravitational pull of orbiting planets. The signals attributed to Gliese 581G were found to be at the edge of detection capabilities and were sometimes indistinguishable from stellar activity noise or data processing artifacts. Some astronomers argued that the initial signal might be a false positive, a result of intrinsic stellar variability rather than a bona fide planet. The ongoing debate highlights the challenges and complexities in exoplanet detection, particularly for planets orbiting close to low-mass stars like red dwarfs, which can have turbulent activity that mimics planetary signals. Despite these disputes, the initial announcement of Gliese 581G spurred significant interest and research into red dwarf systems and the potential for habitable planets around them. It underscored the importance of rigorous confirmation and the need for advanced observational techniques to distinguish genuine exoplanet signals from stellar noise. Ultimately, Gliese 581G remains a contentious topic in the astronomical community. While its existence is still under scrutiny, the intense debate it generated has contributed to refining detection methods and underscoring the cautious optimism required in the exciting field of exoplanetary science. Gliese 581G's orbit within the habitable zone of its parent star, Gliese 581, has significant implications for its potential climate and habitability. Located around 20 light-years away, this red dwarf star's habitable zone is much closer to the star compared to our solar system because red dwarfs are cooler and less luminous than stars like our Sun. Gliese 581G is posited to orbit at a distance that allows for temperatures suitable for liquid water, a critical requirement for life as we understand it. However, orbiting a red dwarf presents unique challenges. Red dwarfs, especially in their younger years, can emit strong stellar flares and high-energy radiation, which could strip away a planet's atmosphere or create harsh surface conditions. Nonetheless, if Gliese 581G possesses a strong magnetic field or a thick atmosphere, it may mitigate some of these harmful effects. Additionally, because Gliese 581G is likely tidally locked, meaning one side of the planet perpetually faces the star while the other side remains in darkness, its climate could be markedly different from Earth's. The day side could experience continuous heating, while the night side might be extremely cold, potentially leading to violent atmospheric circulation patterns as heat attempts to redistribute from the day side to the night side. Interestingly, the terminator line, the twilight zone between the perpetual day and night sides, could provide a more stable and temperate environment. In this region, temperatures might be moderate enough to support liquid water if the atmospheric conditions are right. This would create a narrow band around the planet where life, if it exists, might find a suitable refuge. It's also possible that atmospheric dynamics might help equalize the temperature across the planet, fostering more habitable conditions globally, rather than just in the twilight zone. The precise impact of Gliese 581G's orbit on its climate depends heavily on factors like atmospheric composition, thickness, and the presence of water or other greenhouse gases. Advanced modeling and future observational technologies, perhaps from next-generation telescopes, will be crucial in understanding these dynamics and assessing the true habitability of Gliese 581G. These complexities and uncertainties make Gliese 581G a fascinating subject for studying planetary climates and the diverse environments where life might arise. The discovery of Gliese. 581G primarily utilized the radial velocity method, also known as the Doppler spectroscopy technique. This method involves the detection of tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. As a planet orbits its star, it exerts a gravitational force that causes the star to move in a small orbit of its own. This movement results in shifts in the star's spectral lines due to the Doppler effect. As the star moves toward Earth, its light slightly shifts to the blue end of the spectrum, blue shift, and as it moves away, the light shifts to the red end, red shift. By precisely measuring these periodic shifts in the star's spectrum, astronomers can infer the presence of a planet along with its mass and orbital characteristics. The discovery of Gliese 581G involved long-term monitoring of the star Gliese 581 using high-resolution spectrographs such as the High-Accuracy Radial Velocity Planet Searcher, HARPS, at the European Southern Observatory's La Silla Observatory in Chile and the HIAS instrument at the Keck Observatory in Hawaii. These instruments are among the most sensitive available for detecting small radial velocity variations indicative of low-mass planets. Astronomers observed Gliese 581 over several years, collecting extensive datasets to identify periodic signals that could be attributed to orbiting planets. In the case of Gliese 581G, the team led by Stephen Vogt and R. Paul Butler analyzed these signals and interpreted them as evidence of a planet with a mass approximately 3 to 4 times that of Earth, orbiting within the star's habitable zone. This analysis involved complex data processing and statistical techniques to distinguish potential planetary signals from stellar activity and noise. The announcement in 2010 of Gliese 581G's discovery was based on this detected periodic wobble. However, subsequent observations and analyses have led to debates about the planet's existence, with some researchers suggesting that the signal attributed to Gliese 581G might be a false positive caused by stellar activity or data processing artifacts. Despite these controversies, the radial velocity method remains a cornerstone of exoplanet detection, especially for identifying potentially habitable exoplanets around nearby stars. The existence of Gliese 581G is a subject of intense debate within the astronomical community, with strong arguments both for and against its existence. One of the primary arguments for Gliese 581G's existence comes from the initial data analysis performed by astronomers Stephen Vogt and R. Paul Butler. Using the radial velocity method, they identified periodic signals in the star Gliese 581 that suggested the presence of a planet with a mass 3 to 4 times that of Earth, located in the star's habitable zone. The initial measurements indicated a planet with an orbital period of about 37 days, consistent with the expected gravitational influence of such a planet on its host star. Additionally, the placement of Gliese 581G within the habitable zone of its red dwarf star added significant appeal to its discovery. This zone is critical for the potential presence of liquid water, a key ingredient for life as we understand it. Theoretical models suggested that if confirmed, Gliese 581G could have conditions suitable for liquid water, thereby bolstering arguments for the planet's importance and existence. On the other hand, there are significant arguments against the existence of Gliese 581G. One of the main points of contention is the reliability of the data. Subsequent studies and reanalyses of the original data suggested that the detected signals could be artifacts caused by stellar activity or intrinsic noise within the star's spectral data, rather than indications of a new planet. Red dwarfs like Gliese 581 are known for their magnetic activity and variability, which can create false positive signals in radial velocity measurements. Moreover, multiple independent research teams attempted to confirm the existence of Gliese 581G, but did not find consistent evidence. Studies using similar high-resolution spectrographs, such as HARPS and the HIAS instrument at Keck Observatory, produced results that either failed to detect the planet or attributed the observed signals to stellar dynamics rather than a planetary companion. Critics also pointed out potential flaws in the statistical methods used in the initial discovery, arguing that the algorithms and models employed to filter the data and interpret the signals might not have adequately accounted for the complexities of the stellar activity, leading to overstatements about the presence of a planet. The debate over Gliese 581G exemplifies the challenges faced in exoplanet detection, especially around active stars. While the initial discovery generated significant excitement and optimism about finding potentially habitable planets, the ongoing controversies underscore the need for cautious interpretation and thorough validation using multiple observational techniques and independent verification. Gliese 581G, often referred to as a potential second Earth, is an exoplanet orbiting the red dwarf star Gliese 581 approximately 20 light-years away in the constellation Libra. One of the most compelling features of this distant world is its location within the habitable zone of its parent star. This means it resides in the sweet spot where conditions could allow for the presence of liquid water on its surface, making the planet an intriguing candidate for the possibility of life. The planet's size and mass further add to the intrigue. Gliese 581g is estimated to be around 3 to 4 times the mass of Earth, and because of this, it is expected to have sufficient gravity to maintain an atmosphere. An atmosphere is crucial for regulating temperature, protecting the surface from harmful solar radiation, and potentially providing the right conditions for life as we know it to thrive. Moreover, the planet's orbital period is such that one side might be in perpetual daylight, while the other is in endless night, creating a twilight zone that could harbor relatively stable temperatures. While we have no direct evidence of life on Gliese 581g and several factors, such as its atmospheric composition and surface conditions, remain unknown, the scientific community's interest in this celestial neighbor underscores its potential significance in the ongoing search for extraterrestrial life. HD 189733b, located about 63 light-years from Earth in the constellation Vulpecula, is a gas giant exoplanet known for its astonishingly chaotic and extreme weather patterns. What sets this planet apart is its proximity to its parent star, which results in unfathomably high temperatures averaging around 1000 degrees Celsius on its dayside. This intense heat drives some of the most extreme and violent weather ever observed. One of the most intriguing aspects of HD 189733b is its winds, which can blow at speeds of up to 5,400 miles per hour. To put that in perspective, these winds are 20 times faster than the strongest recorded hurricanes on Earth. These hyperspeed winds whip around the planet, redistributing heat from the blistering day side to the cooler night side in a relentless planet-wide storm. Furthermore, HD 189733b has what some scientists speculate to be rain composed of molten glass. The presence of silicate particles in the atmosphere, likely condensing at high altitudes and being carried by these violent winds, creates a scene almost unimaginable by earthly standards, a sky dripping with scalding glass. These dramatic weather conditions are a result of the planet's large variety of atmospheric particles and its tidal locking, where one side always faces the star, similar to how the moon shows only one face to Earth. This tight embrace with its star ensures that the weather patterns on HD 189733b remain not only unique but also a breathtaking example of how diverse and extreme exoplanet climates can be. HD 189733b was discovered using a method known as the transit technique, which relies on the careful observation of a star's brightness over time. Essentially, astronomers look for periodic dips in the light of a star, which occur when a planet passes or transits in front of it from our vantage point here on Earth. This method was employed successfully for HD 189733b by a team led by French astronomer François Bouchy in 2005. The slight dimming detected in the star HD 189733's light curve indicated the presence of a planet crossing its face, thus revealing its existence. This technique doesn't just confirm the presence of the planet, it also offers valuable information about its size and orbit. For example, the depth and duration of the transit can provide estimates of the planet's radius and its distance from the star. Following the initial discovery, further studies and observations have been conducted, utilizing instruments such as the Hubble Space Telescope and the Spitzer Space Telescope. These observations have helped confirm other aspects, such as the planet's atmospheric characteristics and those aforementioned extreme weather conditions. Thus, the transit method not only led to the discovery of HD 189733b, but also opened the door to a deeper understanding of its exotic nature. HD 189733b stands as one of the most extreme exoplanets ever observed, characterized by a cocktail of hellish conditions that paint a picture far removed from the mild climes of Earth. The planet's close orbit around its parent star causes it to be tidally locked, which means it always shows the same face to the star, creating a blistering day side and a frigid night side. The day side of the planet endures scorching temperatures that can soar to around 1,000 degrees Celsius or approximately 1,800 degrees Fahrenheit. This extreme heat alone sets it apart, contributing to some of the most violent weather in the known universe. Arguably, the most jaw-dropping feature of HD 189733b's weather system is the presence of winds ripping across the planet at speeds up to 5,400 miles per hour, nearly 7 times the speed of sound. These incredible winds likely transport superheated material from the day side to the cooler night side, contributing to an environment of perpetual turbulence. Adding to the nightmarish conditions is the hypothesis of glass rain, tiny silicate particles that condense in the upper atmosphere and are blown around at terrific speeds. Imagine a storm where searing hot glass particles whip through the sky, driven by planets-wide tempests. It's an apocalyptic vision that highlights the sheer diversity of planetary climates in our galaxy. This tempestuous world offers a vivid example of the strange and extreme conditions that exist beyond our own solar system. The color observations of HD 189733b have provided a striking visual component to our understanding of this distant world, offering not just scientific insights, but also a way to bring the alien climate of this exoplanet to life. In July 2013, researchers using the Hubble Space Telescope successfully measured the color of HD 189733b, revealing it to be a deep azure blue, somewhat similar to Earth's appearance from space. However, the reasons behind this coloration are dramatically different. On Earth, our blue appearance is due to the scattering of sunlight by atmospheric molecules and the reflection of sunlight off our oceans. But on HD 189733b, the blue hue is the result of its turbulent atmosphere, filled with silicate particles and possibly molten glass rain, which scatters blue light more efficiently than red. This color measurement is significant for several reasons. Firstly, it marks one of the rare occasions where scientists have been able to directly observe and identify the visible color of an exoplanet. This kind of data adds an invaluable layer of richness to our understanding, making these distant worlds more tangible and less abstract. Secondly, by analyzing the light that passes through and reflects off the planet's atmosphere, scientists can infer critical information about the atmospheric composition and conditions. The blue color specifically suggests the presence of a hazy, cloud-filled atmosphere with particles large enough to scatter light efficiently. This enhances our contextual understanding of the gas giant's eccentric and extreme weather patterns, enriching our broader quest to catalogue and comprehend the myriad types of planetary environments that exist in the universe. The proximity of HD 189733b to its parent star has profound effects on its atmosphere, making it one of the most extreme and dynamic exoplanetary environments observed to date. Situated just 4.7 million miles from its star, by comparison Mercury is about 36 million miles from our Sun, the planet is subjected to intense stellar radiation and gravitational forces. This closeness results in tidal locking, where one hemisphere of the planet perpetually faces the star, experiencing constant day, while the opposite side is locked in perpetual night. This configuration creates a stark temperature gradient between the two hemispheres, with the day side reaching scorching temperatures of up to 1,000 degrees Celsius, while the night side remains significantly cooler. The intense heating on the day side drives extraordinary atmospheric dynamics, including the formation of violent winds that can reach staggering speeds of up to 5,400 miles per hour. These winds play a critical role in redistributing heat, attempting to moderate the extreme temperature differences between the day and night sides. Furthermore, the high-energy radiation from the star can cause significant atmospheric evaporation, particularly of lighter molecules like hydrogen, leading to complex chemical reactions. Observations have indicated that this relentless radiation may even strip away portions of the planet's upper atmosphere, contributing to the exotic and ever-changing nature of HD 189733b's atmospheric conditions. Such proximity to its star means HD 189733b is constantly bombarded with stellar activity, effectively turning it into a chaotic laboratory where scientists can study the effects of extreme radiation on planetary climates. These investigations offer crucial insights, not only into the specific nature of HD 189733b, but also into the broader understanding of atmospheric dynamics and potential habitability of exoplanets orbiting close to their stars. WASP-12b is infamous in the exoplanetary community for its extreme temperatures, earning it the designation as one of the hottest known exoplanets. This scorching world, located approximately 870 light-years away in the Auriga constellation, is a gas giant about 1.8 times the size of Jupiter. The primary reason for its extraordinary heat is its incredibly close orbit to its parent star, WASP-12. This tight proximity results in a very short orbital period of just over 1 Earth day, meaning the planet circles its star in less than 24 hours. Such a close orbit exposes WASP-12b to intense stellar radiation, driving surface temperatures to soar to approximately 2,500 degrees Celsius or about 4,500 degrees Fahrenheit. This searing heat not only makes WASP-12b's atmosphere immensely hot, but also leads to fascinating and rather alarming consequences. The intense radiation from the star causes the planet's atmosphere to puff up and expand, reaching nearly 3 times the radius of Jupiter. This inflated atmosphere is slowly being stripped away by the tidal forces exerted by the star, creating a trailing stream of gas. Essentially, WASP-12b is in a slow but relentless process of atmospheric disintegration, which, given enough time, could completely erode the planet. Such extreme conditions make WASP-12b an important subject of study to understand how close stellar proximity can affect the atmospheric composition and potential lifespan of a planet. Moreover, the high temperatures result in unusual chemical processes within its atmosphere, such as the lack of reflective clouds and the potential presence of exotic materials like titanium oxide. These conditions lead to a low albedo, which causes WASP-12b to absorb rather than reflect most of the incoming stellar radiation, further exacerbating its thermal state. The study of such hellish worlds not only expands our understanding of planetary science, but also serves as a reality check for the diverse and sometimes hostile environments that exist throughout our galaxy. WASP-12b's orbit is particularly unique and notable due to its extreme proximity to its parent star, WASP-12, making it one of the closest orbiting hot Jupiters discovered. The planet orbits its star at a distance of only about 2 million miles, just a fraction of the 28 million miles separating Mercury from our own Sun. This proximity results in an orbit so tight that WASP-12b completes a full revolution around its star in just over 1 Earth day. This orbital period is remarkably short, placing the planet in a perpetual sprint through space, with no respite from the intense gravitational forces and stellar radiation of its host star. Such an exceptionally close orbit leads to several dramatic and scientifically fascinating phenomena. First and foremost, the gravitational interaction between WASP-12b and its star results in severe tidal forces that distort the planet into an elongated, egg-like shape. Much like how the Moon creates tides on Earth, the gravitational pull of WASP-12 on its giant planet causes this pronounced deformation. Furthermore, WASP-12b is also experiencing significant tidal heating, as the friction generated by these tidal forces within the planet contributes to its already sky-high temperatures. In addition to these tidal effects, WASP-12b is in the process of being gradually stripped of its atmosphere due to the intense radiation and gravitational tidal forces from the star. This phenomenon, known as atmospheric escape, forms a trailing stream of gas being siphoned off into space, resembling a comet's tail. Observations indicate that over time, this process could lead to the complete evaporation of the planet's atmosphere, potentially leaving behind only a dense core, or stripping it down to nothing at all. The unique orbit of WASP-12b, with its extreme closeness to its star, provides a natural laboratory for studying the dynamic interactions between stars and their very close-in exoplanets, offering profound insights into the birth, evolution, and eventual fate of such extraordinary planetary systems. WASP-12b was discovered as part of the Wide-Angle Search for Planets (WASP) project, a ground-based survey specifically designed to find exoplanets using the transit method. This method involves monitoring the brightness of thousands of stars and looking for periodic dips in light, which indicate that a planet is passing in front of the star from our vantage point on Earth. It was during such observations in 2008 that astronomers first noticed the telltale signs of WASP-12b. The transit signal showed regular dips in the light from the star WASP-12, occurring roughly every 1.09 days, which pointed to the presence of a large planet with an incredibly short orbital period. Follow-up observations were conducted to confirm the planet's existence using spectroscopic techniques, which analyze the star's light spectrum to detect the gravitational influence of an orbiting planet. These additional measurements allowed scientists to determine key properties of WASP-12b, such as its mass, size, and orbital characteristics. The discovery of WASP-12b was significant not just for the sheer extremity of the planet's conditions, but also for refining the methods used in the search for exoplanets. The combination of the transit method and follow-up spectroscopy affirmed the effectiveness of these techniques in identifying and characterizing distant worlds. Furthermore, WASP-12b's discovery has since spurred a variety of studies into the nature of close-in giant planets, shedding light on the dynamics, composition, and evolution of these so-called hot Jupiters. This groundbreaking find underscored the importance of collaborative astronomical surveys and the continual innovations in the field of exoplanetary science. WASP-12b's atmosphere is incredibly distinctive, marked by some of the most extreme and unusual conditions found on any known exoplanet. One of the most notable features is its blistering temperature. The planet's close proximity to its parent star exposes it to relentless stellar radiation, which heats the atmosphere to around 2,500 degrees Celsius, or about 4,500 degrees Fahrenheit. This scorching heat places WASP-12b among the hottest known exoplanets, leading to a host of dramatic atmospheric phenomena. At such high temperatures, the atmosphere of WASP-12b becomes a cauldron of exotic chemical reactions. One significant consequence is the presence of molecules that wouldn't typically be found in cooler environments. For instance, studies using the Hubble and Spitzer space telescopes have detected evidence of heavy elements like hydrogen cyanide and the potential presence of metals such as titanium oxide, which exist in gaseous form under the extreme conditions. These elements contribute to the atmosphere's low albedo, making the planet one of the darkest objects observed, as it absorbs at least 94% of the light that hits it rather than reflecting it. Perhaps the most dramatically unique characteristic of WASP-12b's atmosphere is its continuing loss into space. Due to the intense radiation and powerful gravitational pull from its parent star, the atmosphere is gradually being stripped away. This process, known as atmospheric escape, creates a stream of gas trailing behind the planet, similar to a comet's tail. Observational data suggest that the planet's atmospheric mass is decreasing significantly over time, pointing towards a future where WASP-12b could be completely denuded of its gaseous envelope. Understanding these features not only provides a window into the severe environmental conditions on WASP-12b, but also offers valuable insights into the life cycle and evolution of exoplanets in similarly hostile orbits. WASP-12b stands out among the class of exoplanets known as hot Jupiters due to several extreme characteristics that give it a unique place in this intriguing category. Hot Jupiters, by definition, are gas giant planets with masses comparable to Jupiter's, but they orbit their parent stars very closely, resulting in very high surface temperatures. However, even when compared to its scorching peers, WASP-12b pushes the boundaries of what we understand about planetary extremities. One of the primary features that set WASP-12b apart is its incredibly close orbital distance from its parent star. Orbiting at merely about 2 million miles away, it completes a revolution in just over one Earth day, subjecting it to intense stellar radiation and immense tidal forces. This proximity not only heats the planet to temperatures around 2,500 degrees Celsius, but also leads to an elongated, football-like shape due to the severe gravitational pull. While other hot Jupiters also suffer from intense heating and tidal forces, WASP-12b's situation is one of the most extreme, fostering one of the hottest and most gravitationally deformed environments observed. Furthermore, WASP-12b experiences rapid atmospheric loss, a phenomenon more pronounced than in many other hot Jupiters. The intense radiation from its star causes the outer layers of the planet's atmosphere to become superheated and expand, resulting in a trailing stream of gas that actively escapes into space. This atmospheric stripping is not as evident in all hot Jupiters, making WASP-12b a crucial subject for studying the long-term evolution and potential dissolution of close-orbiting gas giants. Additionally, its atmosphere has shown chemical signatures like hydrogen cyanide and possible titanium oxide, which are indicators of the high-temperature chemistry that differs from many of its counterparts. While WASP-12b shares common traits with other hot Jupiters, such as high temperatures and significant radiation exposure, its extreme proximity to its star and the accompanying severe tidal and atmospheric effects distinguish it as one of the most extreme examples of this already extraordinary class of exoplanets. This uniqueness not only enriches our understanding of planetary science, but also challenges our expectations of planetary stability and lifespan in such hostile environments. Kepler 452b has earned the nickname Earth's cousin due to several compelling similarities to our home planet, making it one of the most tantalizing exoplanets in the search for potentially habitable worlds. Discovered by NASA's Kepler Space Telescope in 2015, Kepler 452b resides in the habitable zone of its parent star, Kepler 452, which is the region around a star where conditions might be right for liquid water to exist on a planet's surface. This habitable zone is sometimes quaintly described as the Goldilocks zone, neither too hot nor too cold, but just right for supporting life as we understand it. One of the key aspects that make Kepler 452b particularly intriguing is its size and estimated mass. The planet is approximately 1.6 times the diameter of Earth, and while its exact mass is not known, it's estimated to be about 5 times more massive. These dimensions place Kepler 452b in a category of planets known as super-Earths, which are larger than Earth but smaller than the ice giants Uranus and Neptune. Its rocky composition and the gravitational force it could exert suggest that it might have a stable atmosphere capable of supporting various weather patterns and perhaps even life. Moreover, the parent star of Kepler 452b, Kepler 452, is quite similar to our Sun, albeit older, being about 1.5 billion years more advanced in its life cycle. This similarity in stellar type implies that Kepler 452b receives a comparable amount of solar energy to what Earth receives from the Sun, providing another reason to consider the planet as Earth's cousin. Notably, the star's older age suggests that if life were to exist on Kepler 452b, it would have had ample time to potentially develop and evolve, just as life has on Earth. Therefore, while there are many exoplanets discovered to date, Kepler 452b stands out due to its resemblance to Earth in terms of its size, the presence in the habitable zone of a Sun-like star, and the potential for liquid water. These striking similarities provide a captivating glimpse into what other Earth-like worlds might be out there, enriching our understanding of the cosmos and our place within it. Kepler 452b orbits its parent star, Kepler 452, which shares several important characteristics with our own Sun, making the star and planet system an intriguing analogue to our solar system. Kepler 452 is classified as a G-type main sequence star, just like the Sun. This means it shares a similar spectral type, which is essential for assessing the potential habitability of its orbiting planets. Both stars have comparable surface temperatures, with Kepler 452 having a surface temperature of about 5,757 degrees Celsius, which is only slightly higher than the Sun's 5,505 degrees Celsius. Despite these similarities, there are notable differences between the two stars. Kepler 452 is about 1.5 billion years older than the Sun, making it approximately 6 billion years old compared to the Sun's 4.6 billion years. This age difference implies that Kepler 452 has entered a more advanced stage of its stellar life cycle. As stars age, they naturally become brighter and larger due to the accumulation of helium in their cores, which changes their energy output and the conditions in their surrounding habitable zones. Consequently, while Kepler 452 and the Sun are similar types of stars, the aging of Kepler 452 means it is around 10% larger in diameter and about 20% more luminous than the Sun. This increased luminosity impacts Kepler 452 b by bathing it in approximately 10% more energy than Earth receives from the Sun, which could affect the planet's climate and potential habitability. The additional energy may lead to higher surface temperatures and different atmospheric dynamics compared to Earth. However, Kepler 452's stable and long-lived nature provides an extended period for any potential biological processes to develop on Kepler 452 b, assuming other conditions are favorable. Kepler 452 is strikingly similar to the Sun in many respects, such as its spectral type and surface temperature. Yet its advanced age and greater luminosity introduce unique factors that distinguish its planetary system from our own. These differences help scientists understand the various evolutionary paths stars and their planets can take, providing broader insights into the potential for life elsewhere in the galaxy. Kepler 452 b's orbit and size are among the key factors contributing to its reputation as one of the most Earth-like exoplanets discovered. Situated about 1,400 light-years away in the constellation Cygnus, this exoplanet orbits its G-type parent star, Kepler 452, in the so-called habitable zone. This is the region around a star where conditions might be just right to allow for liquid water on a planet's surface, an essential ingredient for life as we know it. One notable characteristic of Kepler 452 b is its orbital period. The planet completes one full orbit around its star in about 385 Earth days, making its year only marginally longer than an Earth year. This relatively similar orbital period means that Kepler 452 b receives sunlight in quantities comparable to Earth, bolstering its potential habitability. The distance between Kepler 452 b and its star is also quite similar to the distance between Earth and the Sun, at about 1.05 astronomical units, AU, where 1 AU is the average distance between Earth and the Sun. This allows for a similar thermal environment which, combined with other factors, might support the presence of liquid water. The size and estimated mass of Kepler 452 b set it apart from Earth, while still providing intriguing similarities. The planet is approximately 1.6 times the diameter of Earth, placing it in the category of super-Earths. Its mass is estimated to be about 5 times that of Earth, though precise measurements are challenging without direct gravitational data. This larger size and mass suggest that Kepler 452 b is likely a rocky planet, similar to Earth, but with a higher gravitational pull. The increased gravity could influence the planet's ability to retain a thick atmosphere, which would play a crucial role in regulating surface temperatures and conditions. Kepler 452 b's orbit and size offer compelling parallels to Earth, with an orbital period and distance from its star that create a similar solar energy environment. Its larger size and mass point towards a potentially rocky composition, making it a prime candidate for further study in the search for life beyond our solar system. These characteristics highlight the planet's potential habitability and fuel ongoing interest and research aimed at unraveling the mysteries of this distant world. Kepler 452 b was discovered through the efforts of NASA's Kepler Space Telescope, an observatory launched in 2009 with the primary mission of identifying Earth-like planets orbiting other stars. The discovery was made using the transit method, a technique where astronomers monitor the brightness of thousands of stars, looking for periodic dips in light that indicate a planet passing or transiting in front of its host star from our viewpoint. Kepler 452 b's detection came after these periodic dips were observed in the light curve of the star, Kepler 452. Detailed analysis showed that the planet completes a transit approximately every 385 days, signifying a year similar in length to that of Earth. The transit method not only reveals the presence of the planet, but also allows scientists to calculate its size and orbital period. The depth and duration of the light dips provide data on the planet's radius, which is about 1.6 times that of Earth, while the periodicity of the transits helps determine its orbital path and distance from the star. Following the initial identification by the Kepler telescope in 2015, additional observations and data analysis were carried out to confirm the discovery and understand the planet's characteristics. This process involved cross-checking the data to rule out other phenomena that could cause similar light dips, such as binary stars or stellar activity. Kepler 452b was part of Kepler's extended mission to find smaller, Earth-sized exoplanets in the habitable zones of their stars, and its discovery was a significant milestone in this ongoing search. The finding was announced on July 23, 2015, during a NASA press conference, capturing widespread interest as Kepler 452b offered one of the most promising Earth-like environments found outside our solar system. The discovery of Kepler 452b underscored the success of the Kepler mission in expanding our understanding of the cosmos and highlighted the potential for finding more planets with conditions conducive to life. This exoplanet remains a prime candidate for studying habitability and the possibility of extraterrestrial life, showcasing the impressive capabilities of the Kepler Space Telescope and the transit method in the field of exoplanetary science. Kepler 452b has captivated the scientific community and the public alike due to its striking similarities to Earth. Discovered by NASA's Kepler Space Telescope, Kepler 452b orbits a star that is remarkably similar to our Sun, with just a 10% increase in size and brightness. This planet is situated within the habitable zone, a cosmic sweet spot where conditions are just right for liquid water to potentially exist on its surface. The distance between Kepler 452b and its star is about the same as that between Earth and the Sun, making it an analogue to our own planet's orbital behavior. The host star of Kepler 452b is also 1.5 billion years older than the Sun, providing a tantalizing hint that life could have had ample time to evolve if conditions were favorable. What magnifies the significance of Kepler 452b is its size. This exoplanet is about 60% larger in diameter than Earth, which puts it in the super-Earth category. Such dimensions suggest that it could have a solid surface and a substantial atmosphere, although we have yet to confirm this. Moreover, its older star may indicate what Earth's own future might look like. Scientists are eager to understand how older, sun-like stars affect their planets, providing insights into both the potential longevity of habitability on Earth and what changes we might expect in our own solar system over billions of years. The discovery of Kepler 452b stands as a milestone in our quest to find other worlds that mirror the conditions of our own, sparking dreams of discovering life beyond our planet. HD 209458b, often known as Osiris, has become a focal point of exoplanet studies due to its unique atmospheric properties. As a hot Jupiter, it orbits extremely close to its parent star, completing a full orbit in just 3.5 Earth days. This proximity subjects the planet to intense stellar radiation, resulting in some extraordinary atmospheric phenomena. One of the most intriguing discoveries about HD 209458b is the detection of a strong atmospheric tail. Much like a comet, this tail is composed of hydrogen gas streaming away from the planet, driven off by the intense heat and stellar wind, showcasing the dynamics of atmospheric escape. Another remarkable feature of HD 209458b's atmosphere is its composition, which includes elements such as carbon and oxygen, manifesting in forms like carbon monoxide and water vapor. Utilizing the Hubble Space Telescope, astronomers have identified a layer of hazes and clouds in its stratosphere, adding complexity to its atmospheric structure. Perhaps most riveting is the detection of sodium in its upper atmosphere, providing insights into the planet's temperature gradient and chemical processes. The presence of such elements indicates that HD 209458b's atmosphere is undergoing intense photochemical reactions, shaped by the extreme conditions surrounding it. These findings not only deepen our understanding of the atmospheric dynamics in hot Jupiters, but also help refine the tools and methods we use to study exoplanetary atmospheres more broadly. HD 209458b is often referred to as Osiris, a moniker that evokes intriguing historical and mythological dimensions. Named after the Egyptian god Osiris, who was associated with the afterlife, resurrection, and the Nile's fertility, this hot Jupiter has resonances of transformation and profound change. The name Osiris was likely chosen due to the planet's striking and dramatic atmospheric features, which include the aforementioned atmospheric tail that gives it a comet-like appearance. This effect mirrors the myth of Osiris, who was dismembered and then resurrected, symbolizing cycles of death and rebirth. Just as Osiris in mythology is a figure of enduring change, HD 209458b undergoes continuous transformation under the intense stellar radiation it receives from its nearby sun. The naming also helps the public and scientific community anthropomorphize and internalize abstract astronomical concepts. By attaching a recognizable name such as Osiris, the planet's unique characteristics are easier to remember and more engaging to discuss. Moreover, in drawing parallels to Osiris's mythological voyage to the underworld and subsequent resurrection, the name poetically captures the dynamic and extreme conditions under which the planet exists. It serves as a reminder of the potent forces at play in the universe and the relentless processes that shape celestial bodies. This mythologically inspired naming tradition enriches our understanding and appreciation of the mysteries of the cosmos, making the study of distant worlds like HD 209458b both a scientific and a cultural exploration. The atmosphere of HD 209458b has significantly deepened our understanding of exoplanets and their complexities. As the first exoplanet where an atmosphere was directly detected, it has paved the way for subsequent studies of other distant worlds. One of the primary contributions is the detailed analysis of atmospheric composition, particularly through the absorption lines detected during the planet's transit across its host star. When HD 209458b passes in front of its star from our vantage point, some of the star's light filters through the planet's atmosphere. By studying the specific wavelengths of light that get absorbed, scientists can identify the atmospheric constituents. This method revealed the presence of sodium as well as traces of hydrogen, carbon, and oxygen. Such detailed chemical profiles help researchers understand the planet's formation history and the physical and chemical processes shaping its atmosphere. Moreover, HD 209458b provided the first observational evidence of atmospheric escape, a phenomenon where stellar radiation and wind strip away the outer layers of an atmosphere. This has profound implications for our understanding of planetary evolution and habitability. Planetary atmospheres are crucial in maintaining surface conditions that could support life, and observing how atmospheres can be lost helps refine models of long-term planetary stability. Additionally, the detection of water vapor hints at the complex interplay between atmospheric chemistry and temperature dynamics, essential for developing comprehensive models of exoplanetary climates. The insights gleaned from HD 209458b have thus set a foundation for atmospheric study techniques and enriched our understanding of how diverse and dynamic exoplanetary environments can be. This knowledge not only enhances our grasp of planets outside our solar system, but also helps inform our theories about our own planet's past, present, and future. HD 209458b stands out as a key target for atmospheric studies, primarily due to a combination of its proximity, size, and the unique characteristics of its orbit. This hot Jupiter orbits very close to its parent star, about 7 million kilometers away, which subjects it to intense stellar radiation and creates extreme atmospheric conditions that are ideal for study. Its substantial size and mass, approximately 0.69 times the mass of Jupiter but with a larger radius, allow for more pronounced atmospheric signals. Additionally, HD 209458b transits its star from our viewpoint on Earth, giving scientists the opportunity to use transmission spectroscopy to analyze its atmospheric composition, chemical dynamics, and temperature profiles in great detail. Moreover, HD 209458b was the first exoplanet where an atmosphere was directly detected, setting a precedent for exoplanetary atmospheric studies. This breakthrough was achieved by observing the planet as it passed in front of its star, known as a transit event. Such events provide an excellent opportunity to study the starlight filtering through the planet's atmosphere, revealing its components through absorption spectroscopy. Hubble Space Telescope's observations have identified elements like sodium, carbon, and oxygen, along with indications of water vapor. This wealth of data not only validates the techniques used to study exoplanetary atmospheres, but also helps refine and calibrate models for future studies. These observations confirm that elements and molecules behave predictably even in extrasolar contexts, thus enhancing our overall understanding of atmospheric science. The robust data and pioneering discoveries associated with HD 209458b continue to make it an indispensable subject for advancing the field of exoplanet research. HD 209458b holds the distinction of being one of the first exoplanets discovered using the transit method, a groundbreaking technique that involves observing periodic dips in the brightness of a star as a planet passes in front of it. Its discovery was announced in 1999, marking a significant milestone in the field of exoplanetary science. The initial detection of HD 209458b was actually made through radial velocity measurements, a method that detects tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. These observations were conducted using ground-based telescopes and suggested the presence of a large, close-orbiting planet. The real breakthrough came when astronomers observed HD 209458b transiting its host star, which provided direct evidence of its existence. A tiny but measurable dip in the star's light confirmed that a planet was indeed passing in front of it. This transit not only confirmed the planet, but also allowed scientists to determine its size and orbital characteristics with a high degree of accuracy. Remarkably, the subsequent transits also facilitated detailed studies of the planet's atmosphere, as starlight passing through HD 209458b's atmosphere during the transit could be analyzed to reveal its composition. This dual discovery method, combining radial velocity and transit observations, established HD 209458b as a pioneering target for exoplanet research, opening new pathways for studying celestial bodies far beyond our own solar system. GJ1214b is often categorized as a super-Earth due to a combination of its size and mass, which are larger than Earth's but significantly smaller than those of gas giants like Jupiter and Saturn. Discovered in 2009 by the Mirth project, GJ1214b orbits a red dwarf star located about 42 light-years from Earth in the constellation Ophiuchus. This exoplanet has a radius about 2.7 times that of Earth and a mass approximately 6.5 times greater, placing it comfortably within the range that defines super-Earths. This classification is crucial because it suggests that GJ1214b has a composition potentially more similar to Earth or Neptune than to the larger gas giants, offering unique insights into the diversity of planetary systems. What truly makes GJ1214b fascinating is its atmosphere, which has been the subject of extensive study since its discovery. Unlike many other exoplanets, GJ1214b exhibits a thick, cloudy atmosphere, possibly rich in water vapor or hydrogen. Spectroscopic observations suggest that it could have a significant amount of water, either in the form of vapor or as part of a deep ocean, leading to the moniker water world. This atmospheric composition challenges existing models and prompts new theories about planet formation and the conditions necessary for habitability. Furthermore, due to its relatively close proximity to Earth, GJ1214b serves as an excellent candidate for detailed atmospheric characterization using both current and next-generation telescopes. These studies aim to decode the complexities of super-Earth atmospheres, enhancing our understanding of planet types that may be more common in the galaxy than previously thought. GJ1214b was discovered using the transit method, a powerful technique that has become one of the primary ways astronomers discover and study exoplanets. The discovery was made by the Mirth project, which utilizes an array of ground-based robotic telescopes designed specifically to monitor nearby small stars for transiting planets. The project focuses on M-dwarf stars, which are smaller and cooler than our Sun, making it easier to detect smaller, Earth-sized planets due to the more pronounced dimming effect when such a planet transits its host star. In December 2009, astronomers observed a periodic dimming of the light from the red dwarf star GJ1214, located about 42 light-years away in the constellation Ophiuchus. This dimming indicated that an object was repeatedly passing in front of the star from our line of sight, causing a brief, regular decrease in brightness. Further observations confirmed that the dimming was due to a planet-sized object transiting the star. The subsequent analysis of the transit data allowed scientists to calculate the planet's size and orbital period, revealing that GJ1214b completes an orbit around its star in just under 38 hours. Following the initial discovery, additional research using both ground-based and space telescopes helped determine the planet's mass and density, confirming it as a super-Earth, with a radius about 2.7 times that of Earth and a mass approximately 6.5 times greater. Its atmosphere was also found to be thick and potentially rich in water or hydrogen, sparking significant interest and follow-up studies. This discovery not only added to the growing list of known exoplanets, but also highlighted the potential of finding Earth-like planets around M-dwarf stars, which are abundant in our galaxy. GJ1214. B's atmosphere is one of its most intriguing features, making it a subject of extensive study since its discovery. One of the most significant aspects is its thick, cloudy nature, which has posed a challenge for scientists attempting to penetrate and understand its composition. Early observations using the Hubble Space Telescope indicated that the planet's atmosphere could be extremely enriched with water vapor or hydrogen. This led to the hypothesis that GJ1214b could be a water world, with a dense and steamy atmosphere, a type of planet not previously well characterized. Detailed spectroscopic studies have revealed a lack of strong features that would otherwise be expected if the atmosphere were clear. This implies that the atmosphere contains a substantial amount of clouds or haze, obscuring the deeper layers from direct observation. The exact composition of these clouds remains uncertain, but they could be made of water droplets, hydrocarbon compounds, or other exotic materials. This thick atmospheric layer makes it difficult to determine precisely what lies below, though the high molecular weight suggested by spectroscopic data points towards a rich, potentially water-heavy atmosphere. The insights gained from studying GJ1214b's atmosphere extend beyond this single exoplanet. It serves as a natural laboratory for understanding the transition between rocky terrestrial planets and larger gaseous worlds. The detection of water vapor or hydrogen supports models predicting a range of planetary outcomes based on formation distance from the host star and subsequent evolutionary processes. Moreover, examining such a cloudy and potentially watery atmosphere helps refine our techniques and instruments for probing the atmospheres of other exoplanets, particularly those in the super-Earth category, which are believed to be quite common in our galaxy. GJ1214b holds a prominent place in exoplanet studies, particularly for understanding super-Earths, because it exemplifies many of the characteristics that make this class of planets intriguing and complex. With its radius approximately 2.7 times that of Earth and a mass around 6.5 times greater, GJ1214b sits neatly within the size range that challenges traditional planet formation models and theories. Its relatively close proximity to Earth, only about 42 light-years, makes it an accessible target for detailed observation using both current and next-generation telescopes. This accessibility allows for repeated and comprehensive studies, which are essential for characterizing the nuanced properties of its atmosphere and composition. One of the pivotal reasons for the focus on GJ1214b is its thick, cloudy atmosphere, which has sparked considerable scientific curiosity. The atmosphere's opacity has provided a natural laboratory for testing and refining the tools and methods used for atmospheric characterization. Studies have pointed to the possibility of a high water content, implying that GJ1214b could be a water world, a type of exoplanet that has not been well characterized prior to its discovery. The presence of water vapor or hydrogen in such abundance could help scientists understand the range of planetary compositions and structures that exist within the super-Earth category. This is crucial because super-Earths are believed to be among the most common types of planets in our galaxy, yet their diversity poses a significant challenge for planetary science. Additionally, GJ-1214b's orbit around a relatively small and dim red dwarf star enables scientists to study the effects of stellar radiation on atmospheric properties. This can provide important insights into the habitability potential of super-Earths orbiting different types of stars. By examining these complex interactions, researchers can better understand how such planets form, evolve, and what conditions might support life. Hence, GJ-1214b is more than just another exoplanet. It is a key to unlocking the secrets of planetary diversity and the various pathways through which super-Earths can develop and sustain different types of atmospheres. The potential for habitability on GJ-1214b is a topic of great interest and speculation among scientists, but current evidence suggests significant challenges. The planet's distinguishing features, its size, mass, and thick atmosphere, present both intriguing possibilities and formidable barriers to life as we know it. With a radius approximately 2.7 times and a mass around 6.5 times that of Earth, GJ-1214b doesn't fall easily into our usual categories of terrestrial or gas giant planets. It likely possesses a substantial gravitational pull, which would affect any potential surface conditions in ways that are difficult to directly compare with Earth. The most promising aspect of GJ-1214b in the context of habitability is its thick, possibly water-rich atmosphere. The idea that it could be a water world, with significant amounts of water vapor or even oceans beneath its cloudy cover, raises the tantalizing possibility that it might possess environments where life could emerge. However, the extreme conditions inferred from current data create a mixed picture. The atmosphere is believed to be dense and steamy, potentially generating surface pressures and temperatures that are much higher than those on Earth. These conditions would likely make it difficult for life, at least as we understand it, to survive or thrive. Adding to the complexity, GJ-1214b orbits a red dwarf star, which, while providing a stable light source, is known for its variability and potential for significant stellar flares. Such flares could strip away atmospheric layers or subject the planet to bursts of harmful radiation. While the thick atmosphere might offer some shielding, it also suggests that the planet's surface, if it exists in a conventional sense, could be inhospitably hot and under immense pressure. Therefore, while GJ-1214b remains more accessible for study and offers valuable insights into the range of planetary environments, its prospects for habitability are currently considered low. The extreme conditions predicted by its atmospheric and physical properties would make it a much different environment from Earth, perhaps more akin to the steamy, high-pressure conditions found in the deep ocean vents of our planet, but on a much larger and more intense scale. Future missions and improved observational techniques may provide more definitive answers, helping to clarify the boundary conditions for habitability both on GJ-1214b and on other super-Earths in the galaxy. LHS-1140b has captured the attention of the scientific community as a prime candidate for habitability for several compelling reasons. Discovered in 2017, it orbits a red dwarf star, LHS-1140, which is located about 41 light-years from Earth, a relatively close distance in cosmic terms. One of its most promising features is its location within the star's habitable zone, where conditions could allow for liquid water to exist on the planet's surface. The importance of liquid water for life as we know it cannot be overstated, as it is a critical solvent in biochemical processes. What sets LHS-1140b apart is its size and density, which suggest a rocky composition similar to that of Earth. The planet has a radius about 1.4 times larger than Earth's and a mass nearly 7 times greater, leading to a higher overall density. This substantial density implies a solid, potentially Earth-like surface, which is a key factor when assessing habitability. The higher gravity potentially aids in maintaining a stable atmosphere over geological timescales, reducing the chance of atmospheric escape and helping to sustain conditions that could support life. Additionally, the host star LHS-1140 is a relatively quiet red dwarf, exhibiting less variability and fewer intense stellar flares compared to other stars of its type. This provides a more stable environment for the planet, reducing the risks associated with harmful radiation that can strip away atmospheres or disrupt potential biological processes. Furthermore, LHS 1140b's slower orbital period of approximately 25 days implies a more moderate climate, increasing the chances of maintaining temperate surface conditions conducive to life. LHS 1140b's favorable position within the habitable zone, coupled with its rocky composition and the relatively calm nature of its host star, combine to make it an excellent candidate for further investigation in the search for habitable exoplanets. Advanced telescopes and observational campaigns are eager to probe its atmosphere for signs of water, oxygen, or other biomarkers that might indicate the potential for life. Indeed, LHS 1140b represents one of the most exciting targets for exoplanetary research, bridging the gap between planetary science and the tantalizing quest to find life beyond Earth. LHS 1140b orbits a red dwarf star named LHS 1140, which significantly influences the planet's potential for supporting life. Red dwarf stars, also known as M-dwarfs, are smaller and cooler than stars like our Sun, emitting less total energy. This particular characteristic places the habitable zone, the region where liquid water can exist, closer to the star. LHS 1140b resides comfortably within this habitable zone, making it a candidate where surface water might be possible. The relatively low energy output of LHS 1140 compared to our Sun suggests that if life-supporting conditions exist, they would be more stable over extended periods, as red dwarfs can sustain their luminosity for billions of years. One of the most crucial aspects affecting LHS 1140b's potential habitability is the calm nature of its host star. Red dwarfs are notorious for their stellar activity, including frequent and powerful flares that can emit harmful radiation. These flares can strip away a planet's atmosphere and pose significant challenges to the development and sustenance of life. However, LHS 1140 has shown to be relatively less active compared to many other red dwarfs, which implies fewer stellar flares and a more stable environment. This relative calmness increases the likelihood that LHS 1140b could retain a stable, life-supporting atmosphere over geological timescales, protecting any potential biological processes from disruptive radiation. Additionally, the infrared wavelengths emitted by red dwarf stars like LHS 1140 can be advantageous for life, as these wavelengths penetrate planetary atmospheres more effectively than ultraviolet or visible light. This efficient energy distribution can lead to warming effects that help maintain liquid water on the surface, thus fostering a potentially habitable environment. In combination with the planet's slow orbital period of about 25 days, which contributes to a balanced distribution of temperature, LHS 1140b's star exerts a mostly benign influence, providing a long-lasting and stable source of energy crucial for habitability. The characteristics of LHS 1140, a relatively quiet, long-lived red dwarf, create favorable conditions for its orbiting planet, LHS 1140b, to potentially support life. The interplay between the planet's position in the habitable zone and the star's stable energy output offers a promising scenario for future explorations, making it an exceptional candidate in the search for life beyond Earth. LHS 1140b boasts intriguing orbital and physical characteristics that make it a particularly compelling object of study in the search for habitable exoplanets. This planet has an orbital period of approximately 25 Earth days, placing it in close proximity to its host star, LHS 1140. Despite this relatively short orbital period, the planet resides within the star's habitable zone, the region where conditions could allow for liquid water to exist on its surface. This fortunate positioning highlights the potential for temperate climates and stability, critical factors for hosting life as we know it. Regarding its size, LHS 1140b is classified as a super-Earth, a type of exoplanet larger than Earth but smaller than the ice giants Uranus and Neptune. Specifically, LHS 1140b has a radius about 1.4 times that of Earth and a mass nearly 6.6 times greater. This combination gives the planet a higher density, suggesting a rocky composition similar to our own planet. The substantial mass and resulting strong gravitational pull likely allow LHS 1140b to maintain a thick atmosphere, enhancing the potential for a stable surface environment that could be conducive to life. Furthermore, the planet's orbit places it at a distance where LHS 1140's less intense radiation provides just enough heat to maintain moderate temperatures without causing the extreme conditions that could strip away its atmosphere or hinder the development of life. The synchronous rotation, common in such close-orbiting planets, can result in one hemisphere perpetually facing the star while the other remains in darkness. However, this can still allow for habitable conditions in the terminator region, the twilight zone between the day and night sides. Together, these orbital and size characteristics make LHS 1140 B not just another super-Earth but a prime candidate for detailed atmospheric studies and habitability assessments. Its location within the habitable zone, combined with a significant rocky mass, sets the stage for a wide range of scientific investigations aimed at understanding the potential for life beyond our own solar system. LHS 1140 B was discovered using the transit method, a technique that has become increasingly pivotal in the identification and study of exoplanets. The transit method involves detecting small dips in the brightness of a star as a planet passes, or transits, in front of it from our perspective on Earth. These periodic dips in brightness can reveal the presence of a planet and provide valuable information about its characteristics, including its size and orbital period. The discovery of LHS 1140 B was announced in 2017 by an international team led by Harvard-Smithsonian Center for Astrophysics astronomers. The MERTH project, which utilizes an array of ground-based robotic telescopes located in Arizona and Chile, played a crucial role in this discovery. MERTH is designed specifically to monitor nearby small red dwarf stars for transiting planets, making it well-suited for identifying Earth-sized and super-Earth planets around these common but relatively dim stars. During the observation campaign, researchers noticed that the star LHS 1140 exhibited repeated, slight dimming events at regular intervals. Detailed analysis confirmed that these dips in brightness were caused by a planet transiting the star every 25 days. Further observations with the HARPS spectrograph at the ESO's La Silla Observatory in Chile enabled the team to measure the planet's radial velocity, thereby determining its mass. The combined data from the transit method and radial velocity measurements revealed that LHS 1140 B has a radius about 1.4 times that of Earth, and a mass approximately 6.6 times greater, making it a rocky super-Earth. The close collaboration between various telescopes and observational techniques underscores the precision and robustness of modern exoplanet discovery methods. The ability to detect such a planet around a relatively faint red dwarf star highlights the growing sophistication in our search for potentially habitable worlds. LHS 1140 B's discovery not only added to the list of intriguing exoplanets, but also provided a prime target for further investigation into the conditions that might support life beyond our solar system. LHS 1140 B, a rocky exoplanet orbiting the red dwarf star LHS 1140, offers a treasure trove of information crucial to our understanding of planetary formation and habitability. Located approximately 40 light-years away in the constellation of Cetus, LHS 1140 B is particularly compelling due to its position within the habitable zone of its star, where conditions are just right for liquid water to exist on its surface. The planet's mass, density, and composition suggest it is predominantly made of rock and could potentially harbor an atmosphere, making it an exceptional candidate for in-depth studies on the potential for life beyond our solar system. One of the most fascinating aspects of LHS 1140 B is its age and stability. The host star, LHS 1140, is a mature, long-lived red dwarf, estimated to be billions of years old. This longevity implies that the planetary environment has had ample time to develop and sustain complex processes that could support life. Furthermore, the reduced stellar radiation from LHS 1140, compared to younger red dwarfs known for their volatile flares, increases the chances that the planet's atmosphere has remained stable over time. These conditions make LHS 1140 B an excellent candidate for future missions to probe its atmosphere for biosignatures, as well as a focal point for theoretical models predicting the environments of similar rocky worlds in the broader universe. 55 Cancri E, a rocky exoplanet located about 40 light-years away in the constellation Cancer, presents some of the most extreme surface conditions known to science. Orbiting its host star, 55 Cancri A, at a blistering close distance of only 0.015 astronomical units, which is approximately 25 times closer than Mercury is to the Sun, 55 Cancri E completes an entire orbit in just about 18 hours. This proximity subjects the planet to intense stellar radiation, resulting in daytime temperatures soaring over 2,000 degrees Celsius, hot enough to melt and vaporize rock. These extreme temperatures, coupled with its high gravity due to a mass roughly 8 times that of Earth, suggest an extraordinary surface environment. It is hypothesized that 55 Cancri E has vast lava oceans or molten rock, potentially mixed with volatile substances like carbon and nitrogen gases. Interestingly, the planet also exhibits a puzzling discrepancy in heat distribution. The day side is far hotter than the night side, indicating complex atmospheric dynamics or partial molten lava flow. The unrelenting heat and high surface pressure create a landscape unlike any found in our solar system, which fuels speculation and scientific interest about its unique geological and possibly volatile-rich composition. As a result, 55 Cancri E serves as a critical natural laboratory, offering insights into the varied and extreme conditions that rocky exoplanets can endure. 55 Cancri E was discovered through the combined efforts of 2 primary detection methods, the radial velocity technique and the transit method. Located in the constellation Cancer, the planet orbits the star 55 Cancri A, part of a binary star system. Its discovery journey began with astronomers using the radial velocity method, which measures the star's wobble caused by gravitational interactions with orbiting planets. In 2004, variations in the star's wobble indicated the presence of a super-Earth-sized planet extremely close to the star, marking the initial identification of 55 Cancri E. Years later, in 2011, the existence of 55 Cancri E was confirmed through the transit method. This technique involves detecting the slight dimming of a star's light as a planet passes, or transits, in front of it from our vantage point on Earth. NASA's Spitzer Space Telescope played a pivotal role in observing these transits, providing crucial data that corroborated its presence and allowed scientists to gather more detailed information about its size, composition, and extreme characteristics. The combination of these methods not only solidified the existence of 55 Cancri E, but also provided a broader understanding of its incredibly short orbital period and harsh surface conditions, making it one of the first super-Earths with such extreme properties discovered. 55 Cancri E exhibits a remarkably distinctive and high-energy orbit around its host star, 55 Cancri A. One of its key orbital features is its extraordinarily close proximity to the star, orbiting at a distance of only about 0.015 astronomical units, which is much closer than Mercury's orbit around our Sun. This proximity results in a year on 55 Cancri E being staggeringly brief, lasting only about 18 Earth hours. Such a short orbital period means that the planet is not just close to its star, but also moving at an incredibly high velocity to complete its orbit so quickly. Another striking aspect of 55 Cancri E's orbit is its presumed tidally locked nature. Tidally locked planets have one side perpetually facing their star, resulting in one hemisphere experiencing constant scorching daylight while the other remains in eternal darkness. This creates extreme temperature gradients between the day and night sides of the planet. Recent studies suggest that the planet may have a dynamic atmosphere or lava flows that circulate heat, which could explain observations showing thermal emission differences between the hemispheres. These unique orbital characteristics, including its closeness to the star, rapid orbital period, and tidal locking, contribute to the extreme conditions on 55 Cancri E and make it an intriguing subject for studying planetary atmospheres and the effects of stellar radiation. 55. Cancri E is renowned for its extreme high temperatures primarily because of its unprecedented closeness to its host star, 55 Cancri A. Orbiting at merely 0.015 astronomical units from its star, equivalent to about 1/20th of the distance between Mercury and the Sun, 55 Cancri E is subjected to intense stellar radiation. This proximity results in surface temperatures that can exceed 2000 degrees Celsius on its dayside, rendering the environment incredibly hostile and far hotter than any planet in our solar system. Additionally, 55 Cancri E's probable tidal locking further exacerbates these extreme conditions. In a tidally locked orbit, one hemisphere of the planet faces the star at all times, continuously absorbing direct and intense stellar heat, while the other hemisphere remains in perpetual darkness. This causes the dayside temperature to skyrocket, producing a stark contrast with the significantly cooler night side. However, intriguing observations have shown that thermal variations between the hemispheres might not be as pronounced as expected, suggesting atmospheric or geological mechanisms, such as supersonic winds or a layer of molten lava, may redistribute some of the heat across the planet. These combined factors, proximity to the star, tidal locking, and potential heat redistribution processes, contribute to the extraordinarily high temperatures that make 55 Cancri E a remarkable example of exoplanetary extremes. 55 Cancri E captivates scientists and astronomers alike for several compelling reasons, making it a fascinating subject for exoplanet studies. First and foremost, its classification as a super-Earth, a rocky planet significantly larger than Earth but smaller than gas giants, opens up a unique window into understanding planetary formation and composition. With a mass about 8 times that of Earth and a diameter twice as large, studying 55 Cancri E allows scientists to explore the properties and behaviors of rocky exoplanets under extreme conditions, offering insights into the diverse range of planetary types in our galaxy. Additionally, 55 Cancri E's extreme proximity to its host star and phenomenally short orbital period provide a natural laboratory for studying the effects of intense stellar radiation and tidal forces on a planet's atmosphere and surface. This planet is believed to endure temperatures exceeding 2000 degrees Celsius on its dayside, which could result in a surface covered with oceans of molten lava or even vaporized rock in its atmosphere. These conditions make it an ideal candidate for observing heat distribution processes, such as potential atmospheric circulation or surface lava flows, that might partially mitigate the dayside and nightside temperature disparity. Moreover, 55 Cancri E's discovery and ongoing observations, using both the radial velocity and transit methods, underscore the importance of multi-technique approaches in exoplanet research. This dual-method discovery not only confirmed the planet's existence but also enriched our understanding of its physical characteristics, driving advancements in observational technology and methodologies. By continuing to study this planet, scientists hope to refine their models of planetary atmospheres, surface compositions, and the potential habitability of other rocky exoplanets in similar extreme environments. Kepler 16b stands out as one of the most intriguing discoveries in the realm of exoplanetary science due to its unique orbit around a binary star system. Located approximately 200 light-years away in the constellation of Cygnus, Kepler 16b orbits 2 stars that dance around each other in a tight 21-day orbit. This planet's peculiar journey through space is reminiscent of the fictional world of Tatooine from the Star Wars saga, offering real proof that planets can indeed orbit 2 stars. This binary system consists of a K-type orange dwarf and a smaller, cooler M-type red dwarf. Kepler 16b itself is a gas giant roughly the size of Saturn with a mass about 1/3 that of Jupiter. It orbits the barycenter, or common center of mass, of the 2 stars at a distance of about 0.7 astronomical units, completing one full orbit in approximately 229 Earth days. The presence of 2 suns means that the planet experiences a shifting light environment, alternating between periods of doubled sunlight and times when one star might partially eclipse the other, casting complex shadows and altering the ambient illumination. The dynamics of this orbit provide an exceptional opportunity to study how a stable planetary orbit can exist in a more complex gravitational field, challenging and extending our understanding of planetary formation and stability in multi-star systems. Kepler 16b's discovery via the transit method, where it crosses in front of both stars as seen from Earth, offers additional layers of observational data. These transit events have allowed scientists to precisely measure the planet's size and orbit, demonstrating the versatility and capability of exoplanet detection methods, even in more convoluted celestial setups. This particular case also provides a tantalizing glimpse into the variety and adaptability of planetary systems, highlighting the potential for diverse environments beyond our own single-star solar system. Kepler 16b was discovered through the diligent observations of NASA's Kepler Space Telescope, an instrument specifically designed to identify exoplanets by detecting minute dips in starlight when a planet crosses or transits its host star. What sets the discovery of Kepler 16b apart is the fact that it was found orbiting not just one star but two, a binary star system. This makes it an exceptional find, as it confirmed that planets can indeed have stable orbits around multiple stars, a scenario previously relegated to science fiction. The discovery process began when the Kepler telescope, which observes thousands of stars simultaneously, recorded periodic dimming in the light from the binary star system 200 light-years away in the constellation Cygnus. These periodic dips indicated the presence of a celestial body passing in front of the stars. Detailed analysis revealed that not only were the two stars periodically eclipsing each other, creating their own dips in brightness, but a third, smaller object was also eclipsing them. This third body was Kepler 16b. Further observations and data analysis confirmed that these transit events were consistent with a planet about the size of Saturn, orbiting the binary stars at a distance of nearly 0.7 astronomical units. Kepler's meticulous light curve measurements allowed astronomers to precisely determine the orbital period of Kepler 16b, which completes a circuit around the binary system in about 229 days. This methodical approach not only validated the existence of Kepler 16b, but also provided critical insights into the stability of planetary orbits in multi-star systems. Kepler 16b is a landmark discovery in the study of binary star systems due to its existence and stability in a dual-star environment, which expands our understanding of where planets can form and endure. Before the discovery of Kepler 16b, the presence of planets in stable orbits around binary stars was largely speculative. Kepler 16b demonstrated that planets could indeed exist in such complex gravitational environments, redefining our notions of planet formation and orbital mechanics. One major aspect that makes Kepler 16b significant is the direct observation of its orbit around two stars. This binary system comprises a K-type orange dwarf and an M-type red dwarf, both smaller and cooler than our Sun. Kepler 16b orbits the barycenter, or common center of mass, of these two stars at a distance of 0.7 astronomical units, completing one orbit in 229 Earth days. The fact that it maintains a stable, almost circular orbit in such a dynamically intricate system offers crucial insights into the resilience and adaptability of planetary orbits in the presence of multiple gravitational influences. This has implications for our understanding of habitable zones, as planets in binary systems might experience different climatic conditions and seasonal variations due to the combined effects of two stars. Moreover, the discovery of Kepler 16b through the transit method, as it crosses in front of both stars, provides a wealth of observational data. This allows scientists to measure the planet's size, mass, and orbital characteristics with high precision. The discovery validates theoretical models predicting the stability of circumbinary planets, and suggests that such systems might be more common than previously thought. Kepler 16b serves as a pivotal benchmark for future searches and studies of exoplanets in binary and even more complex star systems, broadening the potential for diverse planetary environments in our galaxy. The presence of two stars significantly influences the climate of Kepler 16b, creating a complex and dynamic environment that is unlike anything found in our own single-star solar system. Orbiting a binary star system composed of a K-type orange dwarf and an M-type red dwarf, Kepler 16b experiences a unique and variable climate driven by the changing positions and distances of its two suns. One of the most striking effects is the variability in the amount and type of sunlight Kepler 16b receives. As the planet orbits the barycenter of the two stars with a period of 229 Earth days, each star's position relative to the planet changes continually. This means that Kepler 16b can experience periods where both stars illuminate it simultaneously, effectively doubling the amount of sunlight and potentially leading to warmer periods. Conversely, there will be times when the planet is only illuminated by one star or when one star eclipses the other, resulting in reduced sunlight and cooler periods. Such variations can create complex patterns of temperature fluctuations that affect the atmosphere and surface conditions of the planet. Additionally, the dual star system may induce intricate weather patterns and atmospheric dynamics on Kepler 16b. Changes in solar radiation from these two stars could lead to varying wind patterns, cloud formations, and perhaps even storms as the planet's atmosphere responds to the alternating heating effects. Although Kepler 16b is a gas giant and not a terrestrial world, the study of its climate provides valuable insights into the climatic behaviors of exoplanets in binary star systems. Understanding these effects can help scientists predict the potential habitability and atmospheric stability of other planets orbiting multiple stars, offering a broader perspective on the diversity of planetary environments in the universe. Kepler 16b, with its unique orbit around a binary star system, presents an intriguing case for studying planetary environments, but it has limited potential for supporting life as we know it. As a gas giant similar in size to Saturn, Kepler 16b lacks the solid surface that life, particularly life based on Earth's biochemistry, typically requires. Its composition predominantly consists of hydrogen and helium, elements that do not provide the necessary conditions for life forms dependent on liquid water and stable, rocky terrain. The climate on Kepler 16b further diminishes its habitability prospects. The planet's orbit around two stars results in varying light and heat conditions, leading to significant temperature fluctuations. The complex interplay of intense radiation from the K-type and M-type stars likely creates volatile atmospheric conditions, including extreme winds and potentially large storms. The absence of a solid surface combined with instabilities in temperature and climate makes it a harsh and inhospitable environment for Earth-like life. However, the study of Kepler 16b is not without profound implications for the search for extraterrestrial life. It challenges and refines our criteria for habitability and offers insights into the potential for moons orbiting gas giants to support life. If Kepler 16b had large, rocky moons with stable atmospheres, these satellites could, in theory, be candidates for life. Understanding the planet's climatic effects due to its binary stars can inform models that predict the habitability of exomoons in similar systems. Consequently, while Kepler 16b itself may not support life, its discovery expands our knowledge of planetary systems and helps hone our search strategies for more promising candidates in the vast expanse of the galaxy. As we draw our journey through the worlds outside our solar system to a close, we find ourselves standing on the edge of the unknown. The exoplanets we've explored, with their astonishing variety and potential, offer a glimpse into the vast possibilities that lie beyond our home. These distant worlds are more than mere scientific curiosities. They prompt us to ask fundamental questions about our existence. What if we are not alone? What if somewhere out there other beings are looking up at their own night sky, wondering about us? The discoveries we've made so far are just the beginning. Each new exoplanet we find is a chapter in the grand story of the universe, a story that is still being written. The more we learn, the more we realize how much is still left to discover. So as you look up at the night sky tonight, consider this. Nearly every point of light you see is a sun, and around many of those suns, planets are waiting to be explored. The universe is vast, and our journey of discovery is far from over. What other secrets lie hidden among the stars? How will our understanding of life and the cosmos be transformed by the next generation of explorers? Let us know your thoughts and ideas in the comments below. Thanks for watching.